In previous topics, we've looked at energy and energy conversion. You've learned that energy can neither be created nor destroyed, only transformed. That is, converted from one form to another. You've also learned that a number of conversions are necessary in order to transform the chemical energy in fuel to electrical energy. The path that energy follows as it's transformed from chemical energy to thermal energy to mechanical energy to electrical energy is known as an energy flow path. In a power plant, the steam-water cycle, or plant cycle as we'll call it, is an integral part of this flow path. In this unit, we'll look at the plant cycle and the properties of water and steam that make it work. We'll begin by reviewing the energy flow path and then discuss the plant cycle. In other segments, we'll discuss the properties of water, the steam-water mixture, saturated steam, and pressure. Chemical energy in, electrical energy out. Sounds simple enough on the surface, but you and I know that it's much more complicated. As an operator, you need to be concerned with the entire conversion process that we call the energy flow path. Why? Because when you're operating the units in your plant, you're controlling the flow of energy. Let's begin by using this simplified diagram to review some of the things that you already know about the energy flow path, and you'll see what I mean. Then we'll look at the plant cycle. The flow path begins when fuel, such as oil, gas, or coal, is fed into the boiler. The fuel is ignited and burns, transforming its chemical energy into thermal energy. You'll be controlling the amount of thermal energy produced by controlling the flow of fuel into the boiler. The thermal energy is used to produce steam and heat, which is sent to the turbine. The turbine converts the thermal energy into mechanical energy, which causes a rotor in the turbine to turn. Here again, you'll regulate the amount of mechanical energy by controlling the flow of steam through the turbine. The rotation of the rotor drives the generator where the final conversion takes place. The generator converts the mechanical energy into electrical energy, which is then transmitted to the service area through transmission lines. We'll use this simplified diagram to give you an overview of how the plant cycle works. Without it, the transformation of thermal energy to mechanical energy wouldn't occur. As you know, a mixture of fuel and air is ignited in the boiler. As the fuel burns, its chemical energy is converted to thermal energy. Some of the heat is transferred to water in the boiler tubes. During this heat transfer, the water temperature increases and the water vaporizes into steam. The steam is heated further and then flows through a piping system to the turbine. The steam carries the thermal energy from the boiler to the turbine. Steam entering the turbine is directed through the turbine blades. As steam flows through the blades, its thermal energy is converted into mechanical energy, causing the rotating blades and rotor to turn. The turning rotor drives the generator, which converts the mechanical energy into electrical energy. Once steam is passed through the turbine blades, it's exhausted into the condenser. The condenser cools the steam, changing it back to water. The condensate, as it is called, drains into the hot well, where it stays until condensate and feed water pumps send it through a piping system that eventually returns it to the boiler. The plant cycle is a closed loop that allows the same water to be used over and over again. Sometimes the water is used in its liquid state, and sometimes it's used in its vapor state, steam. The plant cycle is dependent on certain properties of water and steam in order to perform its job. Throughout the remainder of this unit, we will look at some of these properties. For now, though, read over the information in your text about the energy flow path and the plant cycle and answer the questions. If you have any questions about this material, clear them up with your instructor before going on. The first segment of this program introduced you to an important part of the energy flow path, the plant cycle, or steam-water cycle as it is sometimes called. The plant cycle is an integral part of the efficient operation of a power plant, and to do its job properly depends on certain properties of water in both its liquid and vaporized state. In this segment, we'll look at 5 properties of water: pressure, temperature, specific heat, specific volume, and enthalpy. You'll learn what they are, their units of measurement, their symbols, and some examples of each of these properties. At first, you may have some difficulty understanding all of the applications of these principles to your job as an operator. Right now, our purpose is to give you an overview of these properties and basic definitions to work with. Later on, we'll look at how the properties of water affect the plant cycle and how a change in one property affects other properties. The first property of water that we need to look at is pressure. Pressure is the measure of force per unit area. So, the basic units for measuring pressure are pounds per square inch, or PSI for short, because, as you know, force can be measured in pounds and area can be measured in square inches. The symbol for pressure is a capital P. Now, pressure is most often measured in relation to one of 2 scales, either the absolute scale or the gauge scale. Pressure measurements using the absolute scale are usually identified by the units PSIA, meaning pounds per square inch absolute. Measurements on the gauge scale use the units PSIG, pounds per square inch gauge. Both scales have equivalent pressure values. The only difference between the absolute scale and the gauge scale is the reference point where their measurements begin. We'll use this drawing to illustrate the reference points for both scales. This line represents all of the possible values for pressure. It begins here, where no pressure is present. The absence of pressure is called a complete vacuum. The scale increases to infinity in this direction. The reference point for the absolute pressure scale begins at this point where no pressure is present. Therefore, 0 PSIA indicates a complete vacuum. The absolute scale increases in this direction. Now, a complete vacuum does not exist naturally at the surface of the Earth. The Earth's surface is constantly under a pressure exerted by air in the atmosphere. Atmospheric pressure changes depending on elevation and weather conditions. In general, we can say that atmospheric pressure at sea level is approximately 14.7 PSIA. The gauge scale uses atmospheric pressure as its reference point. So, at sea level, 14.7 PSIA is equivalent to 0 PSIG. The gauge scale increases in this direction also. What's important for you to understand at this point is how to convert from one scale to the other. Your conversion factor will always be atmospheric pressure. Suppose you have a pressure gauge at sea level that is indicating a reading of 114.7 PSIA. If you want to convert the reading to gauge pressure, you subtract atmospheric pressure. At sea level, the equivalent value on the gauge scale is 100 PSIG. Let's try this example. Another gauge is indicating a pressure of 200 PSIG. If we need to find the equivalent value on the absolute scale at sea level, we add 14.7 PSI to the reading and get 214.7 PSIA. Pressure is a very important property in the power plant, and we'll be discussing it in greater detail in later units. For now, though, let's look at a second property of water, temperature. We talk about temperature all the time. We say it's hot outside or it's freezing in here, but what we really mean by temperature is the measurement of the warmth or coolness of something in relation to a scale. A scale allows us to compare 2 temperatures and describe their differences. Temperature is measured in degrees, usually on either the Fahrenheit or the centigrade scale. Centigrade is also referred to as Celsius. The symbol for temperature is a capital T. The symbol for Fahrenheit is a capital F, and the symbol for centigrade is a capital C. Like the scales for pressure, there are equivalent values for temperatures measured on the 2 temperature scales. However, Unlike the pressure scale, 1 degree Fahrenheit and 1 degree centigrade are not equal. Let's compare both scales and see the difference. The Fahrenheit scale is the one that is probably most familiar to you. Water freezes at 32 degrees on the Fahrenheit scale and boils at 212 degrees. This means that there are 180 Fahrenheit degrees between the freezing point of water and the boiling point of water. The centigrade scale, on the other hand, is based on a scale of 100. Water freezes at 0 degrees centigrade and boils at 100 degrees centigrade. This means there are 100 centigrade degrees between the freezing point of water and the boiling point of water. In order to convert from one temperature scale to another, it's necessary to find the relationship between the scales. We can do this by establishing a ratio. Since there are 100 centigrade degrees and 180 Fahrenheit degrees between the freezing and boiling points of water, our ratio is 100 over 180. Reducing this to its lowest terms, we find the ratio to be 5 to 9. In other words, 5 centigrade degrees is equal to 9 Fahrenheit degrees. We could also say that 1 Fahrenheit degree is equal to 5/9 of a centigrade degree. The formula for converting Fahrenheit measurements to centigrade measurements is as follows. Degrees centigrade are equal to degrees Fahrenheit minus 32 times 5/9. It's necessary to subtract 32 in this formula so that the numbers have a common starting point. Remember, the Fahrenheit scale uses as its reference point 32 degrees, while the starting point for the centigrade is 0 degrees. To have a common starting point, we need to subtract 32. Once this is done, you multiply the result by 5/9 to convert degrees Fahrenheit to degrees centigrade. Let's see how to use this formula by converting 85 degrees Fahrenheit to centigrade. In this example, degrees centigrade are equal to degrees Fahrenheit, 85, minus 32 times 5/9. 85 minus 32 equals 53. We multiply 53 by 5/9 and we get 265 over 9. Doing the division, we find that degrees centigrade are equal to 29.4. So, 85 degrees Fahrenheit is equivalent to 29.4 degrees centigrade. Now, to convert centigrade to Fahrenheit, we must use this formula. Degrees Fahrenheit are equal to 9/5 times the degrees centigrade plus 32. In this case, we have to invert the ratio in order to convert degrees centigrade to degrees Fahrenheit. Then we add 32 degrees Fahrenheit to get our answer. If we have a centigrade measurement of 75 degrees and need to convert it to Fahrenheit, we set it up this way. Degrees Fahrenheit are equal to 9/5 times 75 degrees centigrade plus 32. 75 times 9/5 is equal to 135. Adding 32 to 135, we see that the answer is 167 degrees Fahrenheit. Using these two formulas, you can easily convert from one scale to the other. However, keep in mind that 1 degree on one scale is not equal to 1 degree on the other scale. Now, the temperature of a substance is related to the amount of thermal energy it possesses. Thermal energy has its own units, British thermal units. A British thermal unit, or BTU, is equal to the amount of heat required to raise 1 pound of pure water 1 degree Fahrenheit under standardized conditions. With BTUs in mind, let's look at a third property of water, specific heat. Specific heat is the amount of heat measured in BTUs that is required to raise 1 pound of a substance 1 degree Fahrenheit. The units of measurement for specific heat are BTUs per pound per degree Fahrenheit, and the symbol for specific heat is a small c. For all intents and purposes, we say that the specific heat of water is 1 BTU per pound per degree Fahrenheit. Technically, however, the specific heat of water changes slightly over the range of 32 to 212 degrees Fahrenheit because conditions change. However, since the change is so slight for all but extremely precise calculations, the specific heat of water is considered to be 1 BTU per pound per degree Fahrenheit. If we need to know how much heat is required to change the temperature of 10 pounds of water from 32 degrees Fahrenheit to 50 degrees Fahrenheit, we can use the specific heat of water to figure it out. The difference between 50 degrees and 32 degrees Fahrenheit is 18 degrees. Since the specific heat of water is 1 BTU per pound per degree Fahrenheit, we multiply 18 degrees times 1 BTU per pound per degree Fahrenheit and find that 18 BTUs are required to cause this change in temperature in 1 pound of water. To find the heat necessary to cause the temperature change in 10 pounds of water, we multiply the result, 18 BTUs, by 10 and get 180 BTUs needed to change 10 pounds of water from 32 degrees to 50 degrees Fahrenheit. Another property of water is specific volume. Specific volume is the measure of the amount of space that is occupied by 1 pound of a substance. The units of specific volume are cubic feet per pound, which you'll usually see written this way. The symbol is a small letter V. We'll demonstrate the specific volume of water using this cube. 1 pound of water will occupy the same amount of space as a cube that is approximately 3 inches on each side. You'll learn in later segments that the specific volume of water changes as the other properties of the water change. The final property that we'll look at is enthalpy. Enthalpy is the thermal energy or heat content in a pound of a substance, in this case water. Enthalpy is measured in BTUs per pound, and the symbol for enthalpy is a small h. At 32 degrees Fahrenheit, the enthalpy of water is 0. Enthalpy increases approximately 1 BTU per pound for every 1 degree Fahrenheit increase in temperature. So, the enthalpy of water at 50 degrees Fahrenheit would be about 18 BTUs per pound, and at 212 degrees Fahrenheit, enthalpy is about 180 BTUs per pound. Okay, you now have a general knowledge of 5 properties of water: pressure, temperature, specific heat, specific volume, and enthalpy. You know what they are, the units of measurement for each, the symbol used to identify each one, and you've seen some examples of each. Take some time to read the material in the text and answer the questions. When you come back, we'll see how these properties change in a specific situation. Remember, if you have any questions about this material, ask your instructor to help you. Water has the ability to exist in a variety of states. Here you see it as a liquid. However, if we heat the water sufficiently, it boils and turns into a vapor, steam. By the same token, if we cool water, it turns into a solid, ice. Each of these states, liquid, vapor, solid, may exist at any number of temperatures and pressures. All of these properties, pressure, temperature, specific heat, specific volume, and enthalpy, have different values depending on the state that water is in. These properties also vary within the different states. Now, understanding how the properties of water change is an important aspect of understanding how the plant cycle works. To illustrate the way these properties change, we're going to examine what happens to water as heat is added to it. Beginning with water in a liquid state, we'll see how each of these properties is affected by adding heat. During this segment, we will limit our discussion to water that is under a constant pressure. The pressure we'll use is atmospheric pressure at sea level, 14.7 PSIG. As you probably know, the operating pressure of a typical boiler is much higher than 14.7 PSIG, but the same principles apply in either case. We'll discuss the effects of pressure in a later segment in this unit. Now, there is a range of temperatures at which water exists in a liquid state under atmospheric pressure. On the Fahrenheit scale, which is the one we'll use, this range is between 32 and 212 degrees. On the centigrade scale, the range is between 0 and 100 degrees. The top of this range is called the saturation temperature. At this temperature, water has absorbed as much heat as it can without beginning to boil. If more heat is added, boiling will occur. At temperatures below the saturation temperature, water is often referred to as being subcooled, meaning that the water temperature is below its boiling point. In order to raise the temperature of water to the saturation temperature, heat must be added to it. We'll use this graph to illustrate the process. The horizontal line of the graph indicates the amount of heat in BTUs added to the water. The vertical line indicates the temperature of the water. When water at 32 degrees Fahrenheit is heated, we get a line, which we'll call the process line, that looks like this. As heat is added, the temperature of the water rises until it reaches the saturation temperature. The steepness of the process line is determined by the specific heat of water. As you know, the specific heat of water is approximately 1 BTU per pound per degree Fahrenheit. On the graph, this simply means that when 1 BTU per pound of heat is added to 1 pound of water, the temperature of the water increases 1 degree Fahrenheit. Okay, you've seen how specific heat changes as heat is added to water. Let's look at specific volume. The specific volume of subcooled water changes very little as heat is added. At 32 degrees Fahrenheit, the specific volume of water is approximately 0.0160 cubic feet per pound. At 212 degrees Fahrenheit, the specific volume of water is about 0.0167 cubic feet per pound. So, as you can see, up to the saturation temperature, the volume occupied by water increases only slightly as heat is added. Now that we've looked at how adding heat affects specific heat and specific volume, let's turn our attention to enthalpy. As you recall, enthalpy is the heat contained in a pound of water. At 32 degrees Fahrenheit, the enthalpy we start out with is 0. As heat is added to the water, enthalpy increases by about 1 BTU per pound for every degree Fahrenheit that the temperature is increased. The reason for this is that the specific heat of water is 1 BTU per pound per degree Fahrenheit. Because the enthalpy of water changes in this relatively regular manner, it makes it fairly easy to calculate the enthalpy of water at any temperature between 32 and 212 degrees. All that is necessary to get a close approximation of enthalpy is to subtract 32 from the actual temperature. For example, the enthalpy of water at 100 degrees Fahrenheit would be 68 BTUs per pound, because 100 minus 32 is 68. The units for enthalpy are BTUs per pound. Let's try this one. The temperature of water is 212 degrees Fahrenheit. What's the enthalpy? Well, 212 minus 32 is 180. So, according to our method, the enthalpy of water at 212 degrees Fahrenheit is 180 BTUs per pound. Now, if we perform carefully controlled laboratory tests on water at 212 degrees Fahrenheit, we'd find that the enthalpy of the water is actually closer to 180.2 BTUs per pound. The reason that the value is slightly larger is the fact that the specific heat of water is not always exactly equal to 1. For our calculations, we'll use the value 180.2 for the enthalpy of water at 212 degrees Fahrenheit. However, for most practical applications, using the value of 180 BTUs per pound for the enthalpy of water at 212 degrees Fahrenheit at atmospheric pressure is close enough. Well, you've now seen what happens to each of the properties when heat is added to water. And remember, The pressure exerted on the water in all of the examples in this segment was atmospheric pressure. You've also seen that as heat is added, the temperature of the water increases up to the saturation temperature, 212 degrees Fahrenheit, at a rate of about 1 BTU per pound per degree Fahrenheit. We've also discussed the fact that the specific volume of subcooled water doesn't change much as heat is added. Finally, we've looked at the enthalpy of water and one method of calculating it at any point between 32 and 212 degrees Fahrenheit. Before going on to discuss what happens at temperatures above this range, when boiling takes over, read the material in the text and answer the questions at the end of the segment. If you have any questions about subcooled water, clear them up with your instructor before going on. So far, you've seen what happens to the properties of water at atmospheric pressure when heat is added to bring the water up to the saturation temperature. We've been discussing only half of what happens to water in a boiler. First, it's heated to saturation temperature, then it's boiled. In this segment, we'll look at what happens to the properties of water as heat is added beyond the saturation temperature. We'll follow the process until all of the water has boiled to steam. Let's start by considering this flask of boiling water. Now, we've all seen water boil at atmospheric pressure, but let's take a look at what is really going on. As heat is added to the flask, the water temperature increases. At the saturation temperature, 212 degrees Fahrenheit, the water has absorbed as much heat as it can without boiling. Beyond the saturation temperature, bubbles begin to form and rise to the surface. This is due to water changing from a liquid state to a vapor state. During the boiling process, water enters what we'll call a transition zone. The transition zone is a unique situation where water and steam can coexist. Instead of having all water or all steam, we have a steam-water mixture. The pressure in this example will remain the same, 14.7 PSIG. The temperature also remains the same, 212 degrees Fahrenheit, because all additional heat is used to convert water into steam. Now, during our explanation of this unique situation and how the properties of water are affected by it, we'll make a distinction between saturated water and saturated steam. Saturated water is water at the saturation temperature that is not boiling. Saturated steam is steam at the saturation temperature that has no water present. In both cases, the saturation temperature is the same, 212 degrees Fahrenheit. The amount of heat required to turn a quantity of saturated water completely into steam is called the latent heat of vaporization. At atmospheric pressure, the latent heat of vaporization is 970.3 BTUs per pound. 970.3 BTUs per pound is a value you should remember. What it means is that for every pound of water, 970.3 BTUs must be added to turn the water completely into steam. In the plant, latent heat of vaporization is added to water in the boiler to convert it to steam. By the same token, to convert steam back into water, 970.3 BTUs must be removed from every pound of steam. In the plant, latent heat of vaporization is removed in the main condenser in order to convert the steam exhausting from the turbine back into water. Since the temperature of the steam-water mixture is not changing, specific heat does not change while water is converted to steam. However, specific volume is greatly affected by the boiling process. As you'll recall, the specific volume of subcooled water changed very little as heat was added. The specific volume of water at 212 degrees Fahrenheit is about 0.0167 cubic feet per pound. The specific volume of saturated steam, however, is about 26.8 cubic feet per pound. This is quite a dramatic increase in specific volume. To put this change into perspective, let's take a look at this cube that measures 3 inches on a side. As you know, this cube represents the approximate volume of 1 pound of water at the saturation temperature. Compare it to this cube that is roughly 3 feet on a side. This cube represents the approximate volume of 1 pound of saturated steam at atmospheric pressure. As you can see, the increase in specific volume is quite significant. In fact, 1 pound of saturated steam is about 1,600 times the volume of 1 pound of saturated water. This increase in volume is important to the plant because the expanding steam creates pressure in the boiler. Likewise, the condenser depends on the condensing of the steam back to water to create a vacuum. Okay, now that we've looked at pressure, temperature, specific heat, and specific volume, let's look at the enthalpy values of saturated steam. We said that saturated water at atmospheric pressure has an enthalpy of 180.2 BTUs per pound. We also said that the amount of additional heat needed to change saturated water completely into saturated steam, the latent heat of vaporization, is 970.3 BTUs per pound. Adding these values together gives us 1,150.5 BTUs per pound as the enthalpy of saturated steam. In other words, 1,150.5 BTUs of heat per pound of water is required to heat 1 pound of water from 32 degrees Fahrenheit to 212 degrees Fahrenheit and to convert it completely into steam at atmospheric pressure. We've discussed the fact that throughout the boiling process we have a steam-water mixture. We can further discuss this mixture in terms of moisture content and quality. Moisture content is the percentage of water in the steam-water mixture. Quality, on the other hand, is the percentage of steam in the steam-water mixture. The moisture content of the steam-water mixture is the number of pounds of water divided by the number of pounds of steam-water mixture multiplied by 100. So, if there were 10 pounds of a steam-water mixture and 9 pounds of it was water, the moisture content would be 9 divided by 10 times 100, which is 90%. By the same token, the quality of the steam-water mixture is the amount of steam in pounds divided by the pounds of steam-water mixture and multiplied by 100. In the mixture we just talked about, there were 9 pounds of water in a 10-pound steam-water mixture. That means that 1 pound is steam. So the quality of the mixture is 1 divided by 10 times 100, which is 10%. Using this same example, we can use moisture content and quality to determine the specific volume of the steam-water mixture. In general terms, what we'll do is determine how much the specific volume of saturated water and saturated steam contribute to the specific volume of the mixture. To do this, we use this formula. Specific volume, small v, is equal to the specific volume of saturated water times the moisture content plus the specific volume of saturated steam times the quality. In our previous example, the steam-water mixture had a 90% moisture content and a 10% quality. Plugging these figures into our formula, we get specific volume of the steam-water mixture equal to 90% of the specific volume of saturated water, 0.0167, plus 10% of the specific volume of steam, 26.8. Doing the math, we get a specific volume of approximately 2.70 cubic feet per pound. Using this same example, we can also calculate the enthalpy of the steam-water mixture. First, multiply the enthalpy of saturated water by the moisture content. The enthalpy of saturated water is 180.2 BTUs per pound, and the moisture content in our example is 90%. 180.2 BTUs per pound times 90% gives us about 162.2 BTUs per pound. This is the value for the enthalpy of the water in the steam-water mixture. To determine the enthalpy of the steam in the steam-water mixture, we multiply the enthalpy of saturated steam, 1,150.5 BTUs per pound, times the quality, 10%, and find that the enthalpy of the steam in the steam-water mixture is about 115.0 BTUs per pound. The enthalpy of the steam-water mixture is then found by adding these two values together. 162.2 plus 115.0 equals 277.2 BTUs per pound. So, the enthalpy of the steam-water mixture is 277.2 BTUs per pound. An understanding of the concepts of moisture content and quality are important when analyzing the plant cycle. Examples of where these conditions exist are the boiler drum in drum-type boilers and in the condenser. In later segments, we'll see other applications of these concepts in the plant cycle. For now, though, let's review what we've covered so far. We started with water at 32 degrees Fahrenheit and 14.7 PSIA. We added 180.2 BTUs per pound to get the water to the saturation temperature. At the saturation temperature, we continue to add heat to the water to get it to boil. This is called latent heat of vaporization, and at 14.7 PSIA is equal to 970.3 BTUs per pound. The total enthalpy, or heat content, of saturated steam at 14.7 PSIA is 1,150.5 BTUs per pound. Before we go on to discuss what happens to the properties of water when still more heat is added to saturated steam, take some time to read over this material in the text and answer the questions at the end of the segment. If you have any problems with this material, clear them up with your instructor before going on. In the last two segments of this unit, we've seen how the properties of water are affected when heat is added to water that is under a constant pressure of 14.7 PSIA. We began with subcooled water at 32 degrees Fahrenheit and found that 180.2 BTUs of heat per pound of water was required to bring water to the saturation temperature. An additional 970.3 BTUs per pound, the latent heat of vaporization, was required to change saturated water into saturated steam. In short, a total of 1,150.5 BTUs of heat had to be added to 1 pound of water to bring it from 32 degrees Fahrenheit to saturated steam at 212 degrees Fahrenheit. In this segment, we'll continue to add heat to saturated steam to increase its temperature beyond the saturation temperature. Steam heated above the saturated temperature is called superheated steam. Superheated steam is a very important part of the plant cycle because it carries thermal energy from the boiler to the turbine. Now, in reality, superheated steam leaving the boiler is under a much higher pressure than 14.7 PSIA. However, in principle, the effects of the properties on water are the same. We'll continue to hold pressure at 14.7 PSIA to teach you these effects. In the final segment of this unit, we'll look at how pressure affects the properties in the plant cycle. For now, though, let's look at the effect additional heat has on saturated steam. Returning to our graph, notice that when heat is added to saturated steam, its temperature increases. If we add 90 BTUs per pound, for example, the temperature of the saturated steam increases to approximately 400 degrees Fahrenheit. This temperature increase is governed by specific heat. You'll recall that while in the transition zone, specific heat was not a factor, because all additional heat added to the steam-water mixture was used to change water into steam. When all water has turned to steam, however, additional heat increases the temperature of the steam. Notice also that the process line for saturated steam is much steeper than the process line for subcooled water. This is because it takes less heat to increase the temperature of saturated steam. Where it took 1 BTU per pound of subcooled water to increase its temperature 1 degree Fahrenheit, it takes about 1/2 BTU per pound to increase the temperature of saturated steam 1 degree Fahrenheit. The specific heat of saturated steam, then, is approximately 0.5 BTUs per pound per degree Fahrenheit. Increasing the temperature of saturated steam also has a significant effect on the specific volume of the steam. You know that 1 pound of steam at 14.7 PSIA and 212 degrees Fahrenheit occupies a volume of 26.8 cubic feet per pound. If we add 384 BTUs per pound to saturated steam, we'll raise its temperature to 1,000 degrees Fahrenheit, but we'll also increase its specific volume to 59.1 cubic feet per pound. In other words, the volume of the steam more than doubles. Enthalpy also continues to increase as heat is added to saturated steam. At the saturation temperature, steam has an enthalpy of 1,150.5 BTUs per pound. At 1,000 degrees Fahrenheit, the enthalpy of superheated steam is 1,534.5 BTUs per pound. This represents an increase of 384 BTUs per pound above the enthalpy of saturated steam. So, when water has turned completely into steam, adding more heat to the steam will increase both the specific volume and the enthalpy of the steam. As we said earlier, we've held the pressure in our examples throughout the last three segments constant at 14.7 PSIA to help teach you the principles of what happens when heat is added to water. Increased pressure has a significant effect on these properties, as you'll see in the next segment. Before we get into that, let's review what we've covered so far. Water at 32 degrees Fahrenheit requires 180.2 BTUs per pound to bring it to the saturation temperature. 970.3 additional BTUs per pound are required to change the saturated water into steam. This additional heat is called the latent heat of vaporization, which is the heat required to change all of the water into steam. A total of 1,150.5 BTUs per pound is needed to bring water at 32 degrees Fahrenheit and 14.7 PSIA to saturated steam at 212 degrees Fahrenheit and 14.7 PSIA. Beyond this point, as heat is added, the enthalpy of the steam continues to increase and the steam becomes superheated. The enthalpy of superheated steam at 1,000 degrees Fahrenheit is 1,534.5 BTUs per pound. Take some time to review this material in your text and answer the questions. If you are having any trouble following any of these points, ask your instructor to help you before going on. By this point, you have a good understanding of how the properties of water are affected when heat is added to water at a constant pressure. You followed water from the subcooled region through the latent heat of vaporization to the region of superheated steam. Throughout our discussion thus far, we've kept the pressure exerted on the water at 14.7 PSIA to make our examples easy to follow. However, in the plant cycle, you'll be dealing with water and steam that are under a wide range of pressures. In this segment, we'll look at pressure and the effect it has on the properties of water. On a graph, the process that we've been discussing looks like this. At 14.7 PSIA, subcooled water rises to the saturation temperature in this manner. During boiling, the process line moves in this direction until all water has been converted into saturated steam. The line then moves this way into the superheated region. Let's see what a similar process looks like when pressure is reduced to 1 PSIA. The process line moves in the same manner as before, through the subcooled region. The only difference is the boiling point occurs at a lower temperature. During boiling, the line follows a similar path as before. The same is true as the line moves into the superheated region. As you have probably noted, the process line for both 14.7 PSIA and 1 PSIA are quite similar. Let's look at the process line for a higher pressure. This time, the pressure is 200 PSIA. The line in the subcooled region rises as before, with the exception that boiling occurs at a higher temperature. During boiling, the line moves in this direction, and in the superheated region, the line moves in this direction. Again, the process line is similar to what we've seen before. Let's look at two other pressures. Here's the process line for 1,000 PSIA. Here's the line for 2,500 PSIA. Notice that the process lines for all of the pressures that we've looked at are similar. The major difference between them is the saturation temperature and the size of the transition zone. Now, the pressures that we've used here were chosen at random from a number of possible pressures. If we plot all of the possible points where water becomes saturated and steam becomes saturated, we get two curves that look like this. Let's take a closer look at these curves. As you know, the portion of the process line in the transition zone is the latent heat of vaporization. Latent heat of vaporization is the amount of heat that must be added to saturated water to completely change it into steam. At atmospheric pressure, the latent heat of vaporization is 970.3 BTUs per pound. On the graph, notice that as pressure increases, the line gets shorter. The values for latent heat continue to decrease as pressure increases, until pressure reaches 3,208 PSIG at 705.47 degrees Fahrenheit. At this temperature and pressure, the value of latent heat of vaporization is 0. This point is called the critical point. At or above the critical point, there is no observable difference between water and steam. Water turns continuously into steam without going through a transition zone. Some power plant boilers operate at pressures above 3,208 PSIG. Such boilers are referred to as supercritical because they operate above the critical point. When water is converted to steam in a supercritical boiler, the process line looks like this. It passes over the critical point and continues on into the superheated region. Now that we've looked at how changes in pressure affect temperature, let's move on to how pressure affects specific heat, specific volume, and enthalpy. The values for the specific heat of water and steam change very little with changes in pressure. For example, the specific heat of water at atmospheric pressure is approximately 1 BTU per pound per degree Fahrenheit. The specific heat of water at 1,000 PSIG is also approximately 1 BTU per pound per degree Fahrenheit. Likewise, the specific heat of saturated steam at atmospheric pressure is about 0.5 BTUs per pound per degree Fahrenheit. While it tends to be a little higher near the saturation temperature, at high temperature and pressures, the specific heat of saturated steam remains approximately 0.5 BTUs per pound per degree Fahrenheit. The specific volume undergoes some changes in the superheated region as pressure increases, but very little change in the subcooled region. You'll recall that at 14.7 PSIG, the specific volume of subcooled water changed very little until it began to boil. This is also true for pressures above or below 14.7 PSIG. The reason for this is water is virtually incompressible. We can demonstrate what this means by using this example. Here we have an illustration of a cylinder filled with 1 pound of water. This piston can be used to exert a pressure on the water. At 14.7 PSIG, the water only compressed this far. Additional pressure will cause almost no change in the volume of the water. This is what we mean when we say water is virtually incompressible. Now, when water is turned into steam, the situation changes. Steam, being a vapor, is compressible. For example, at 14.7 PSIG, 1 pound of steam looks like this. Watch what happens to the volume of steam as pressure is increased. As we raise the pressure to 200 PSIG, steam becomes more compressed. At 1,000 PSIG, more compression takes place. And at 2,500 PSIG, still more compression takes place. We can conclude from this that as pressure increases, the specific volume of steam decreases. The final property that we need to consider is enthalpy. Enthalpy does not significantly increase or decrease as pressure changes. However, as pressure changes, there may be a change in the state of water or steam, as well as a change in the moisture content and quality of the steam-water mixture. Returning to our graph, between the beginning of the transition zone when water becomes saturated and the end of the transition zone when steam becomes saturated, we have a continual change in the steam-water mixture from high moisture content to high quality. When water first begins to boil, the moisture content is 100% and the quality is 0. As boiling continues, the percentages change until at the end of the transition zone, quality is 100% and moisture content is 0. Any change in the pressure being exerted on the steam-water mixture will change the percentages. For example, at this point in the transition zone at 14.7 PSIA, we have a moisture content of about 50% and a quality of about 50%. If we raise the pressure to 200 PSIA, the percentages change. Now the moisture content is about 60% and the quality is around 40%. By the same token, if we lower pressure to 1 PSIA, the moisture content decreases to about 40% and the quality increases to nearly 60%. In the same manner, an increase or decrease in pressure can change the state of water. For example, at this point at 200 PSIA, water is just ready to boil. If we decrease pressure to 14.7 PSIA, some of the water becomes steam. The steam is now part of a steam-water mixture in the transition zone. Decreasing pressure further to 1 PSIA, more of the water turns to steam and the quality of steam-water mixture increases. Changes in moisture and quality and the state that water is in are very important to you as an operator. If, for example, there is a sudden drop in pressure, the quality of the steam-water mixture increases. As you know, the specific volume of the steam in the steam-water mixture can increase as much as 1,600 times. This change in volume could cause serious damage to piping and possibly to equipment. In later units, we'll discuss further the effects that rapid changes in pressure can have on the operation of a power plant. For now, though, let's review what we've covered in this unit. We began by introducing you to pressure, temperature, specific heat, specific volume, and enthalpy, and showed what happens to these properties as heat is added to subcooled water at a constant pressure, bringing it to the saturation temperature. We continued to see the effects additional heat has on the properties of water during boiling and into the superheated region. Finally, we looked at what happens when the pressure exerted on the water and steam increases or decreases. This unit has laid the groundwork for your understanding of the plant cycle. In future units, we will show you practical applications of the properties of water and steam to the plant cycle. For now, though, read the remainder of the material in this unit and answer the questions. If you have any trouble understanding the material we've covered, ask your instructor to help you.